Williams. I am the space science architect for the Air Force Office of Scientific Research. And I want to welcome you to our Chief Scientist Distinguished Lecture Series, where we bring world-leading researchers from across the globe to share the latest discoveries from their field. Today we have Professor Delores Knipp from the University of Colorado Boulder, and she's going to speak to us about her work in space weather, which not only significantly impacts space, but also impacts life on Earth, such as producing electromagnetic fields that can disrupt power, causing significant power outages. Every time I hear something from Delores, I can't sleep for a few days, and I expect nothing else from today. And Dr. Julie Moses, our Space Science Program Officer, will introduce Delores to all of us. Julie has known Delores since she was in graduate school. But before I turn it over to Dr. Moses, we would like to pay tribute to the victims and honor the survivors of the September 11th, 2001 terror attacks that killed nearly 3,000 people and injured thousands at the World Trade Center, the Pentagon, and in Somerset County, Pennsylvania. This horrific attack affected all of our lives, and each year on the anniversary, commemorations are held across the world. We will observe a moment of silence to remember all of the victims, their survivors, and all that were damaged by this act of terrorism. Thank you. So I don't see Dr. Moses on. Cindy, is that true that she hasn't been able to get on?
Correct, unless she is calling from the caller that's here, but I don't know if that is her.
Okay.
Ending in 159.
Let's see. No, she ends in 2958.
Copy that.
So, okay, well, I'm going to go ahead and introduce Professor Delores J. Knipp from the University of Colorado at Boulder. Delores is a research professor at the Smead Aerospace Engineering Science Department at the University of Colorado Boulder, also called CU Boulder. She earned her doctorate degree in atmospheric and space physics from the University of California, Los Angeles in 1989. Her career spans more than 30 years as an active duty Air Force officer and civilian professor at the U.S. Air Force Academy, where she taught physics, meteorology, and astronomy, followed by more than a decade of teaching and research at CU Boulder. During that time, she wrote the first space weather textbook for upper division undergraduates entitled Understanding Space Weather and the Physics Behind It. From 2014 to 2019, Professor Knipp was the editor-in-chief for the American Geophysical Union's Space Weather Journal. Professor Knipp's research focuses on the space environment and the atmospheric and solar events that disturb it. She works with students to investigate methods for describing how structures on the sun produce disturbances in near-Earth space, specifying satellite drag, improving scientific use of the space environment measurements from commercial, DoD, NASA, and international space missions, describing the effects of extreme space weather at Earth, and developing educational material related to space weather. She studies historical space weather events to understand the impacts these events have had on society and the U.S. military. In 2019, she became a fellow of the American Meteorological Society. Professor Knipp is participating in NASA-sponsored efforts to prepare historical space weather data sets for machine learning extreme detection. And then I will also add that Delores Knipp presented some of the space weather past events and some of her work to General Kreider, who was the Chief Technology and Information Officer for the Space Force. And General Kreider said she could have stayed there all day listening to Delores because she had no idea how important space weather is. And actually, Julie, Dr. Moses is connecting. Let's see if, I guess, well, we'll just turn it over to you, Dr. Knipp. Thank you.
Okay. Well, thank you for the introduction, and it was not lost on me that I was going to be presenting on a day that would be one with significant remembrance. And I can tell you that I distinctly remember I was going into the Air Force Academy to teach, of all things, a space weather class on this day 22 years ago. And what an amazing and disturbing change that has brought to us, but we are all on the other side of it, and we have found ways to move on. So I am really thankful for that. Let me go ahead and share screen. And I will move
Looks
my,
good, ma'am. We're up
okay,
and running.
sounds good. And I'm just going to claim as much real estate as I can on my window here. So I am so honored to be asked to talk about the thing that has basically been a driver of my life since the Air Force, since I joined the Air Force Academy as a weather officer. And about 1 year into that assignment, the department chair from the physics department came to me and said, well, you may not know this, but we offer to sponsor each year one member of the department for a PhD. And I kind of thought, why is he telling me that? And I didn't get it, but he finally did bring around that they were considering to sponsor me, and was I interested? And if yes, I needed to make a decision in 24 hours. And so that was a true life-changing situation that has sent life and hopefully for the good of my students into a completely different arc. So I'd like to talk a little bit about balancing what I call an unbalanced threat. And of course, my throat's going to go dry here. So the threat is associated with the electromagnetic and mass that is emitted from the sun in very episodic events. If you look over on this left diagram, you'll see the sun, a collage of pictures, 10 years of looking at from space, at looking at active regions on the sun, and you'll see the two bands that are that develop over time. They start from the north, from the polar regions or mid-latitudes, and essentially descend into and connect over the equator. And in the process of doing that, there is a tremendous amount of magnetic energy that is shed. And that magnetic energy comes out in the form of electromagnetic radiation, solar flares. It comes out in mass, magnetized mass that we call coronal mass ejections. And it also comes out via the combination of the two of those under circumstances where we have extremely fast events. It comes out in the form of very limited but very energetic solar particles. And those energetic particles and the solar flares and radio bursts that come with them are going to be a primary topic of discussions today. But I do want to also acknowledge that space weather is absolutely beautiful. I've had the chance to see the aurora once in my life, and as I'm nearing my end of formal teaching career, it is my plan to go on plenty of trips to view this from this kind of scene from below. And let's see. There we go. So, quick overview. I want to tell the audience a little bit about space weather. Very, very quick overview in just 4 slides, and then talk more about the history of space weather, both on a kind of a grand scale and the scale that's going to lead into the discussion of events that I have listed here. I'd also like to tell you a little bit about the progress we've made, how we're achieving balance, but what still gives me pause, and then some final thoughts. So this little diagram that you see over here on the right was one that was drawn for me by the Australian Broadcasting Corporation after an Australian scientist and I had essentially written a very interesting and thought-provoking article about the events in 1972. And I did not know about those events, but Brian Fraser from Australia was a postdoc at what is now Space Weather Prediction Center. And he had heard that just off on the sides, listening to bits and pieces of conversations, that there had been some very big concerns in 1972 about a space weather storm. And I'm going to tell you a little bit more about that. So what is space weather? Well, it's events and disturbances that originate at the sun for the most part, that propagate rapidly into and interact with geospace. There are impacts on humans, signals, engineered systems. For the most part, the impacts on humans before we had engineered systems was to generally terrorize the populace with auroral displays that seemed unexplainable. What we now know is that these activities are driven by active regions on the sun, which are NISTs, a really complex magnetism that sometimes just cannot be contained, and they fuel eruptions. They're flares, energetic particles, and ejecta. And in some case, the ones I'll tell you about today, those are multiple interacting bursts and ejections. And then I've kind of listed a laundry list here of what's affected. Certainly Earth's atmosphere. Conductors, we're no longer worrying much about telegraphs, but power grids definitely are still on our radar. Speaking of radar, communication and navigation, all kinds of radar signals they're used to track spacecraft, any kind of radio communication, and GNSS or GPS signals, as you may know them. Humans and hardware, even in space and other planets. And this all takes place over the course of minutes to hours to days, and sometimes weeks, if there are recurring active regions. This is a diagram that I hold dear and near. It's probably one that was created, or I helped create way back in the day in the early 90s, talking about these different aspects of space weather, mostly episodic, these flares and radio bursts. Their energy arrives in 8 minutes and generally has a duration of a few hours, couple of hours, but sometimes longer. There are also, coming with those flares, these bursts of material from the sun, giant plasma bubbles sent out at supersonic speeds. If they are in fact moving faster than information can be carried in the medium, they create a shock. That is usually the case. And between the flares and the shocks from these coronal mass ejections, we get a phenomenon called solar energetic particle events. And those are the ones that will be the topic of some of my first, but mostly my second case study. These magnetic fields and plasma, these are the aspects of space weather that create the beautiful aurora that I just showed you, but are also a bane to people who are working in radio communication, trying to maintain track of satellites, talk to satellites, share information, and of course the power grids and the GNSS signals that I've mentioned before. So space weather is cyclic, but it's also episodic. So I've just picked out a diagram here from Ian Richardson and Hilary Kane that was published well over a decade ago, but it was so nice and clean, I thought I would use it. People have been counting sunspots since Galileo created the telescope and allowed the sun to be viewed, and got into a lot of trouble for indicating that there were in fact spots on the sun rather than clouds orbiting the sun. But we now know that those numbers of sunspots rise and fall. We've been counting them. We are now in our 25th solar cycle, so we go back a very long time, which I'll show you in a moment. We know that as these sunspot numbers rise and fall, the number of geomagnetic storms and the number of days with aurora rise and fall as well. But if you think you're noticing that there's a little bit of time lag here with these ups and downs, you're correct. It is after solar max and going into the declining phase, where essentially those bands that I showed you on the very first slide are interacting more with each other, that we tend to get the most geomagnetic activity. So we're a couple years away from that, but even on the rise of the solar cycles, we definitely see a lot more activity than we've seen in the solar min. These blue lines here indicate kind of minor storms, ones that you might see maybe one every other week, or maybe not quite so often in solar min. And then these extreme storms, the ones that I tend to look at, we maybe get 4 per solar cycle. We hardly had any in solar cycle 24, but it looks like solar cycle 25 is perhaps going to make up for that. I also want to point out to you that we have only really been diligently monitoring the sun and able to see its output since about 1977, when we put spacecraft on orbit upstream from Earth and started making measurements of these mass ejections and the material that surrounded them. And we were also able then to take pictures, not only just reporting that there had been some kind of a burst of energy, but actually locate it. And to our dismay, to find out that when those two emissions sometimes put themselves together, they could create a snowstorm in space, where under some circumstances, we would not even be able to see these images because there were so many energetic particles interacting with the telescope tubes to essentially make the instruments blind. When that happens, you know you've got a really bad storm coming in. And of course, that's what's interesting to me. So rather than put a movie in and risk it not showing, I decided to come back to this graphic because it's going to be something that goes that shows up in various slides throughout. And just to point out to you that it's not just all about the sun and the mass ejecta and the shock and particles, but what all of those do to interact with Earth's magnetic field. And Earth's magnetic field is basically a dipole. It's amazingly good at protecting us from the onslaught of these things from the sun, but from time to time, even the dipole has to flex. Well, it does flex all the time, and it gets stretched out. And rather than being just a dipole, it gets kind of squashed on the day side and stretched way out on the night side, which is a location where energy can get stored, where particles can be drawn from the upper atmosphere and energized back in this region. So during magnetic storms, we're really now starting to understand that Earth's atmosphere plays a role in both enhancing and to some degree modulating what goes on. Those particles, after they're energized, can be very, very energetic if they're especially hydrogen atoms. They can get energized to the point that they interact with the dipole and create essentially rings or toruses of energetic particles called the radiation belts. They're semi-permanent features, but can really be enhanced during geomagnetic storms. And then the other thing is these beautiful, beautiful, what I consider to be beautiful aurora, but I can tell you that there has been times in human history that people thought they were anything but beautiful. So let me kind of move on to that idea. Great aurora, especially the ones that went very far equatorward, were ones that used to terrify political leaders and rulers, almost always in thinking that this was some kind of a bad omen. And so as far back as 567 BC, and actually I now know about 100 years earlier, there were glyphs, essentially in this case being etched into clay to report that on the night of the 29th of March, which now correlates to 12 to 13 March in current time, 567, there was a red glare that flared up in the west, and this was seen from Babylon. So indeed a very equatorward location. And this scribe did not just type this out on an iPad. This had to be written in clay and reported to the king. This went on for many years, many centuries. Ultimately, people were able to make better drawings, and here's one from medieval times in the 1500s. Again, this great red aurora with white streaks. Here's probably someone a little bit more knowledgeable, several people more knowledgeable over here on the left, but these four blokes over here on the lower right, they think this is not going to end well. So it was in general for the uninformed population, which was most of the population, something that was very scary. Great red aurora that are seen at very low magnetic latitudes are very noticeable. They're very rare, but they are in fact scary, not only from the point of view that someone who's reporting them has probably never seen them, but also because they are indicative of the strengths of storms that are probably going to interact with technology systems. So let me just kind of bring you to the space weather record that my graduate students and I have, or my undergrads even, have been working on. We went back and kind of surveyed literature for 500 years and asked, as a proxy for these great storms, how often do we see red aurora below 30 degrees magnetic? And the rule had to be that we're seen with the naked human eye, not with a camera. And so I've documented these, and this is probably a severe underdocumentation because, as you might imagine, not a lot of records have survived in this early time frame. But we do know that there were events like the one in 1770, where for 9 days, low latitude red aurora were reported out of Japan. During this time frame, not a lot of technology, but now if we move into the early 1800s, we start to see all of these things showing up in bright blue here, the first commercial telegraph, the first battery, the first radio signal. And now what we're in is a situation where those energetic particles, because they are charged, they do move around field lines, they are able to get in and interact with our technology. You'll also notice that there are a lot more reports, which I believe due to two reasons. First of all, we have better archives of the most recent. And secondly, we simply had a lot more interaction and people were always wanting to know what was going on. Additionally, the sun went through a number of very weak activity periods in the first half of this time frame, whereas it came roaring back in the 1800s, notably with 1859, when there was the first great space weather storm. The most recent one that we've had, where we can document with human eyes for red aurora below 30 degrees magnetic, was in 1989. That was the same event that caused the 9-hour collapse of the Hydro-Quebec power grid, and also a time frame where we lost about 2,000 objects from the NORAD space catalog, which had to be acquired over the upcoming weeks. A lot of effort. And this is the thing I'm going to focus on for the rest of the presentation. So let's talk about space weather in the space age. I'm going to kind of look at that record by just the total number of objects that are orbiting Earth. And you notice we start here in about 1957, where there was one. It was called Sputnik. And then after a lot of upheaval on both Eastern, Western blocks and anyone who supported them, the humans really got their act together and started putting a lot of material into space to kind of discover and see what was out there, a final frontier, if you will. As is often the case, you go exploring and you start to kind of leave a mess behind. And what you see here is this growing number of things in orbit is not necessarily the number of active spacecraft we have, but it's going up because of the number of fragmentation debris or mission-related debris. You'll see some of these very sharp changes here. Huge increases in the amount of material orbiting Earth because of an anti-satellite test or because of a collision. And now we're also seeing a big uptick in the number of things orbiting Earth because of mega-constellation launches. The vast majority of these are in low Earth orbit. Air Force for a long time now, Space Force has maintained a catalog, meaning that we keep track of where these things are, where they are at the moment, where they're forecast to go, to some degree where they've been. So we have people very busy monitoring not only the real active things, but also these growing debris fields. And as I mentioned, the number of spacecraft that are now on orbit is really, really markedly increased. And our idea that space was kind of infinite, at least in the low Earth regime, has pretty much gone away. We have to think about collisions. Space operators think about collisions on a daily basis. In some cases, there are kind of collision avoidance or collision warnings, if you will, going out sometimes on the order of several hundred per day. I'm going to talk a little bit about these events right here with the arrows. Those are the ones with the publicly known events where this space catalog that we've maintained for so long had to be reassembled due to some kind of space weather event. I'm not going to talk about all of them, but in particular, these first three in red. So let's go back to the Cold War. And in particular, in the mid-1960s, that's when lots of spacecraft were in fact going up to do various things, to explore, to reconnoiter, to surveil. In 1967, early spring of 1967, there was a lot of political and military back and forth related to the borders associated with Israel. A lot of incursions from Syria, which generated response from Israel. And this went back and forth the better part of the spring. In mid-May of 1967, President Nasser of Egypt ousted the UN peacekeepers from the Sinai, that region that basically kept Egypt and Israel separated, and managed to deploy tens of thousands of troops in the Sinai. Ostensibly because he believed that Israel was getting ready to attack. On the 22nd of May, he went further with saber rattling and essentially decided to block the Tiran Straits, which is the only access to the Pacific Ocean and the trade there that the Israelis would have. And the Israelis, not surprisingly, viewed that as an act of war. So things became more and more tense, and the world was watching and waiting, and reconnaissance spacecraft were on the scene. At the very same time, there was a huge active region on the sun, MAC region 8188. Thankfully, we had recently trained space weather forecasters who had moved in residence to NORAD Cheyenne Mountain Complex. We had people who knew what the sun could do. And it's absolutely crucial that you know that, because we have a militarily tense time. We have the sun acting up at the beginning of a solar cycle, a little bit unusual. And on the launch pad, because of all of these concerns about what was going on in the Middle East, the Soviets had a reconnaissance spacecraft ready to launch, and it did launch at about 1300 on the 22nd of May. On the US launch pad was a spacecraft with similar purpose. It launched on the order of 5 to 6 hours later. Interestingly enough, it carried, I think purely by circumstance, that one of these was going to carry some kind of acceleration measurements to determine what the low Earth atmosphere looked like, and this was the mission. It carried something called LOGAX, Low G Accelerometer Calibration System. It's for that reason that we know a lot about what happened during that time frame. So the sun on the 23rd of May, not really even 24 hours after those two spacecraft had launched, let loose with an incredible flare, one of the largest that had been seen in certainly a decade. And we were able, because we were in space, we were able to now monitor these in terms of X-ray. It was the beginning of our ability to describe flares in terms of their X-ray output. Tremendous amount of energy coming out in the extreme ultraviolet, which heats the upper atmosphere, which is relevant here. But the biggest part of this story is the extreme radio frequency interference that was generated out of this particular event at about 1840 UT. It created more radio frequency interference than we had ever seen, 1,000 times above background. And it was very broad spectrum. It included the spectrum for which our ballistic missile early warning system was operating. And even though this happened at about noon over the US, and the radars were looking up over the pole, the radiation intensity, the radio frequency interference was so intense that it basically got into the back lobes and the side lobes of these radars and effectively jammed the Cold War radars. And I can tell you from talking with Soviet emigres that they also know that that event helped fund Soviet solar radio observatories for well over a decade after that happened. The situation was, because of the very militarily and politically intense time, that, and without knowing, at least some members or aspects of our military, without knowing that a flare had just gone off, actually interpreted this as enemy jamming, also viewed to be an act of war. And that jamming basically prevented us from understanding, from looking over the poles, knowing what was going on. We knew, however, that spacecraft had launched. And so that apparent act of jamming caused SAC. And to a large degree, the fighters that were in support of NORAD to, at the very minimum, go to aircraft, sit at the end of the runway. It was a very busy time on a lot of runways at US Air Force bases. The concern there, and what finally brought things to kind of a calming situation, was that we did have a space weather forecaster who was able to at least get to NORAD commanders and let them know that this was probably the space environment and less likely to actually be a full-scale act of jamming. And so that was taken into consideration. But as you might guess, the word didn't get out to everyone. What apparently did hold and prevent us from launching aircraft was the realization that the radio situation was so bad that if aircraft launched, we would not be able to be in contact with crews. And certainly it would be seen by the Eastern Bloc as a lot of aircraft launching all at once, which could have been considered provocative. None of that happened. Everybody stayed on the ground with the exception of the normal patrols, of which there were many, but it was indeed a very, very tense time. And I'll just tell you that I've been able to talk with the forecaster on that day. His name was Lee Snyder. At least a couple of years ago, he and I had a conversation, and he told me a lot more about that day. So we essentially got the situation under control to the best of our ability with the radio bursts and the extreme flares, but the incoming energy from the shock and the plasma bubble that had been sent directed bang on to Earth arrived within a couple of days. And as a result, that low G accelerometer system observed extraordinary geomagnetic storm impacts at very low altitudes, below 250 kilometers. We also found that there were intense waves of disturbances. We know that the temperature in the upper atmosphere increased 500 degrees in almost a spike. And for that reason, tracking of resident space objects on LEO were essentially disrupted. Thereafter, NORAD had to essentially reestablish at least half of the catalog. And that was not a lot, but there were not a lot of instrumentation to help do that. All of that transpired even before the early June start of the 6-day Arab-Israeli war. I am of the opinion that if that had actually happened during the war, things could have been in a very, very difficult state. So let me just tell you a little bit about that LEO environment. This is information that was in classified documents for a while, but after about 4 years, it made its way out in a NASA tech report. What we were able to see during this time frame was a huge increase in geomagnetic activity. It essentially pegged a significant increase in solar output. And then as the LOGAX experiment was flying along just for a ride on that reconnaissance spacecraft, we were able to see over the course of days how the atmosphere heated and expanded and essentially caused a need for there to be orbital adjustments to keep that spacecraft in orbit for its primary mission. We actually were able to, NASA was able to work the data and find that there from the equator to the pole, there were a whole series of waves. And this is the ratio of the actual density to the model density, sometimes going up by a factor of 2, almost like running across a speed bump, if you will, on the road or a series of speed bumps. So this was our first look at just what the upper atmosphere looked like. And as I mentioned, there were a lot of spacecraft that were not immediately locatable, and this generated a need for improvements in density forecasts, and those improvements essentially carry on, that need carries on through today, especially with the number of large constellations that are being launched. So I'll give you a little space weather scorecard here. In the last 20 to 25 years, we've actually created scales for space weather. They're not the best, they're undergoing improvement, but they're scales like 1 to 5, much like the hurricanes. This event was at the top in terms of the geomagnetic significance, very near the top in terms of flares. And actually, this doesn't look like it, but it's pretty close to the top in terms of energetic particles as well. We've actually never hit an S5 event. So for a short amount of time, when so many other things were going on, there were enough particles coming into the polar cap regions to essentially prevent radio communication, completely aside from the fact that there was radio interference. And I'll just leave you with this kind of list of things that happened that we learned about. We had one of our very first geosynchronous satellites on orbit, and it found itself, even in geosynchronous orbit, outside in the solar wind. The boundary between the Earth's field and the solar wind is usually between 9 and 10 Earth radii. And on the day side, that boundary came into within 6.6 Earth radii, a really remarkable situation. It was after that time the Air Force decided to put significant investments into space environment support services, from which I ultimately benefited. I was probably one of the last PhDs of the crowd in the 80s, 70s and 80s that went through a very short, intense 3-year program for studies in space environment. I'll now turn very quickly to August 72. This is an event that still confounds us. I have a paper in press right now. We know that out of this event, during the downturn of that solar cycle that produced the one in events in 67, there was a flare that essentially saturated the new space-based detectors that we had launched. There were multiple ejecta. Some at the beginning were slow because they were running into the interplanetary medium. But they were clearing the path for subsequent ejecta. And to this day, the speed of 2,000 kilometers per second for that tertiary ejecta was the fastest ever recorded, although there's now some hints that we maybe saw one of these in 1940. It created an extreme solar energetic particle event that I am now able to tell you a little bit about. Effects everywhere, even changing the chemistry of the upper atmosphere. Again, compression of Earth's magnetic field, and it set Earth's magnetic field ringing with spikes and pulsations. The pulsations were large enough to essentially detonate about 4,000 sea mines that were magnetically sensitive off of the coast of Vietnam as we were still in the middle of prosecuting the Vietnam War. This event is more intense. It was faster, but it brought in a train of these bubbles of material with shocks in front of them. Those interactions created huge amplifications and amplifications in the solar energetic particles that got trapped in between the shocks and the prior CMEs. Here is from I believe this was a NASA spacecraft that was actually launched just prior to the event. And this is as close to an S5 as we have ever, S5 level as we have ever gotten. Many sensors were getting false readings, no readings at all. In particular, there was a set of spacecraft called Vela, and one of their primary jobs was to monitor for nuclear tests. And in this particular event, I believe it was Vela 6. Here's the logbook, which has just been declassified as of last year, where there's a little notation in here that says biggest event in history. Well, what would be the ramifications of at least the biggest event in history for the Vela spacecraft? They were charged with helping the US essentially verify nuclear treaties and activities and locate it if there was such an activity going on. So they were the monitors from space. They essentially were designed to measure thermal neutron flux. Those are neutral particles that are emitted during nuclear explosions. But this particular spacecraft, the instrumentation could be ghosted by these solar protons, of which I have just shown you we had hit the biggest event in history. So there was a lot of activity. I had colleagues who told me they were called out in the middle of the night to help sort out what was going on. These interacting shocks and CMEs essentially saturated those monitors. And over the course of the next 90 days, after things finally did settle down, about a week and a half later, their entire life was essentially recoding and reprogramming the output from this spacecraft to discriminate between true thermal neutrons and the energetic protons that the sun was throwing at us that day. It was a significant effort. Finally, the last thing, and probably much more of concern to the US Navy, was, as I mentioned, when that the shocked event hit, all of a sudden the magnetic field at Earth, and this is from the Philippines, started ringing, oscillating back and forth to the amount of oscillations and with a signal that was very much aligned with a signal that would be interpreted as a small ship or boat laden with war material going past the mine, in which case it was programmed to detonate. So here are the quotes that come from some of the materials that I've read. The destructor minefield along Haiphong and to the south was actually swept by this solar geomagnetic storm. During the first few weeks of August, at that time, the resulting chain of events caused the premature detonation of 4,000 magnetically sensitive sea mines. There were Navy observing spacecraft up in the early morning hours and saw these events. 24 of them were reported to go in 30 seconds. And the assessment was that the entire minefield had been swept. So the Navy was essentially mandated to re-establish all of those mines. And Mr. Gonzalez, who wrote the article that I read about that, said that he really felt his troops deserved a medal for what they did within 2 months. It was not just in the low latitude regions of the eastern portions of the world. In US and especially over Canada, those same spikes of geomagnetic activity that didn't even really get reported in the power grids. The power grids are pretty limited at 72 up in central Saskatchewan and Alberta. But as we go further south, you can see here are the list that Jeff Love has put together of all of the power grid anomalies, most of which occurred within about a 1 hour time frame. But because the field was oscillating, I've heard stories. My husband's from the Dakotas, and I've heard the stories about essentially local power system operators up all night just trying to keep the grid stable. Apparently, it did not hit a major metropolitan area, although there were a lot of anomalies along the Washington, D.C., New York corridor. There was none that was long lasting enough to essentially bring down the power grid, which at that time was much more separated. Now that we have these chains of long conductors, I suspect that this would have been an event for the record books. I will just close this out by telling you that we had a number of ways of monitoring the space environment. We would use cameras to watch the trajectory of spacecraft, and from that basically infer how their motions were changing. Same kinds of activity, May 1967, August 1972. However, we had fewer of them, so the record is not quite as good. But this event has the same level of perturbation, almost an order of magnitude change of solar wind densities as we saw in May of 1967. So my understanding of this was that these were essentially equal types of storms occurring with just in 5 years of each other. I've been looking at what those signals look like, and I've gone back and asked a colleague of mine from Space Environment Technology. We had some ideas what we should be searching for in the most recent record. And so we went back to an event in 2015, looked at now the model output, they're much better, by the way, of neutral density, and we found an almost order of magnitude increase for an event that probably has very similar characteristics of these. So we're going to go back and really dig into those and try and find out with all of the coupled models what actually happens to create these orders of magnitude density perturbations throughout the atmosphere. So scorecard again, it was big. Biggest geomagnetic storms that we could put on a scale. And actually, because this one was so big, it motivates some of my colleagues in Europe to actually go back and re-examine this scale. And there is a new set of scales coming out where we probably would say, oh, that was a G6 storm. It was, the flares were off the scale, and practically so were the energetic particles as well. There were all kinds of unexpected ground faults, problems with space-based monitoring, and satellite drag space tracking difficulties were just legion. So I'll now go really quickly through just 2 more events, not in the same detail, but now we've moved to March 89. It's an event that may be in the history, memorable history for some of you. And we're actually now watching these active regions rotate across the sun. When this particular event left loose, though, however, it was right in this gap between March 10th and March 13th. We do know that there were huge X-rays. We know that there were a series of train of CMEs again. Here's the power outage map. And we now know, we knew immediately that Hydro-Quebec suffered a 9-hour power outage. The Great Red Aurora, the ones that I mentioned to that my students and I studied, were seen at latitudes less than 30 degrees magnetic, all the way down to Mexico. And as you might expect, we were much more engaged in space all kinds of comms, satellite anomalies, a spacecraft tumbling, and at least 1,000 resident space objects that had to be found. And the U.S. Air Force Air University actually has this event in some of its training material where we show the pulse of geomagnetic activity and then the week-long attempt to go find, categorize, and label, if you will, those spacecraft, where they are and where they're going. Scorecard, pretty much the same. But what's a little different about this was with the problems with power grids, there became a growth in not only DoD, but in civilian investments as well. It was a fits and starts, but it was one that clearly persisted. And so now comes something that I haven't mentioned before, and I won't mention much again, but every time there's a disruption on all of these scales, our ionosphere, essentially our medium, which we used for radio communications, is greatly disturbed. And that was very, very well noted during that time. This was also the time that the US military was using GNSS or GPS at the time, but this general public did not have access to it. Big event that happened in 1983. Well, now the public had access, scientists had access, and this event essentially created huge instabilities in the Earth's ionized atmosphere. Again, it was the same level as the 1989 event. Curiously, no great red aurora reported at very low latitudes, but I will simply tell you that the research that my graduate students and I are doing based on old archived DMSP data suggests that there were great red aurora. It should have been visible over the pretty empty Indian Ocean. And that will be a topic of a future presentation, I'm sure, at various meetings. Space weather at that point became recognized as both a national and international team sport, if you will. So what's the commonality here? This is, I think, where I'll kind of finish up. What is the commonality in these extreme space weather events? We start with very complex active regions on the sun that have a large reservoir of energy. They have a specific kind of configuration that space weather prediction and other entities use. It looks like alphabet soup. This means that those regions are capable of producing trains of ejections, ejecta, and the first one will probably be slow, pile up material in front of it, but it clears the path for the second and third. And with the machine learning work that I've been doing with my students now, what we are finding is that these events that consist of 1, 2, 3, and sometimes 4 in a row are the ones that are very, very much associated with the kinds of events that I have just described. So we're now able to see, based on monitoring upstream, get some idea of what it is that might be coming at us, but we still are working a lot of machine learning activity to try and go through immense amounts of data to find out when these regions are going to develop and when they're just going to reach the tipping point. And I think I want to save a little bit of time here for questions. So I'm just going to call this good. I had more examples, but I just want to tell you that we have made tremendous, tremendous strides since 1989 and 2003. And we've got so much data that we would like to gather. I'm on national committees talking about what kind of data should be gathering, but the avocation of my life is going back and looking at our old DoD data, Defense Meteorological Satellite Program, to essentially go through decades of data at a time to find out what causes these great storms. So with that, I will stop share, and maybe there will be a few questions.
Thank you, Dr. Knipp. We appreciate you so much. For our viewers, the recording will be posted to our YouTube channel once we received our cleared and approval status of that. And I know that Dr. Moses has had some technical difficulties. I believe she is here. I just don't know which phone number is hers to activate. But at this time, I can certainly go in the order of the Q&A, or if you would like to look at the Q&A and answer the ones that that most interest you in the time that we have. However you would like to do it, ma'am.
Okay. Well, I am going to address this very first question that says, have you heard of the Carrington event? What would be the impact of a similar event today? And the answer is, yes, I have heard of a Carrington event. We have a paper that is currently just about to exit the copy edit stage that shows that there was a second one within about 15 years. These Carrington events are the ones, the one in 1859, where the flare was so strong that humans were able to see the flare with their eyes and then connect with the very fast geomagnetic perturbations, the geomagnetic storm and the great red aurora that came with it. So yes, I've heard of it. And one of the things that I have learned and really trying to convey is that was not a singular event. There have been 3 of those within about 60 years of that time frame. And the events of a similar situation today would probably not be pretty, especially in terms of the low Earth orbit environment, because it is now so very congested, and we still don't have effective ways of monitoring it very well. So I will leave it at that. And let's see. So there's Michael Horner asking, do galactic cosmic rays only come from within the Milky Way, or can they originate in other galaxies? They are what we call ubiquitous. They come from all directions, and we think well beyond the Milky Way. And so yes, galactic cosmic rays are usually so ubiquitous that they're considered background. But if you're going into space, well, that's kind of a different matter, because they carry a lot of energy and they can damage DNA. And let's see. Paul O'Brien's one. Paul is a colleague of mine, also from UCLA. Paul O'Brien wants to know, why did the waves propagate from the equator to the pole in 1967? Typically, the energy goes the other way. And indeed, I think that was the case. I have not looked in detail at that particular case study. But what I am thinking is, in the way that was presented in the 1970s, it simply looks like the waves were propagating from the equator to the pole. In fact, that energy deposition is primarily at the pole, and the energy should propagate from the poles to the equator, actually cross the equator from both poles, and then do a significant enhancement in the equatorial regions, which makes for some very interesting forecasting challenges.
Excellent. I think we may be able to squeeze in 1 or 2 more, maybe.
Yeah, there's a question in space weather more extreme in MEO and GEO orbits than in LEO. It's simply different. Most of the MEO and GEO, well, MEO, if you're going to have those spacecraft maybe dipping down, but I'm thinking of highly elliptical orbits, but the MEO and GEO orbits suffer a lot more from spacecraft charging, from interactions with energetic particles. It is just as damaging, as mission ending as with the LEO situation. The reason I've kind of harped on LEO is because we now have so many spacecraft in that congested environment.
Wonderful. Let's see. We have 2 more minutes left.
So there's a question, is it possible to put a team together for crossover data regarding the correlation of climate alteration and our comms systems disruption? How can we organize that knowledge for immediate actionable data? Boy, there's someone after my own my heart. I've spent a lot of time advising NASA, DoD, and National Science Foundation as a member of the Space Weather Advisory Committee, and that is, along with my concerns about LEO orbit, essentially one of the top priorities is that we have to, not only do we live in a world of sparse data, but the data that we do take so often just kind of gets left behind. And we really need to be making the best possible use of that data. And that is a high-ranking recommendation in our Space Weather Advisory Group that I think was briefed to on the Hill earlier this week or last.
Wonderful. Well, again, thank you, Dr. Knipp, for this wonderful talk. We do have a couple other questions, but in the interest of staying on time and honorable to everybody that is here, just want to say thank you. Thank you for sharing your information with us. Again, I do apologize for Dr. Moses' connectivity issue, but I'm sure she is saying thank you, thank you, thank you, thank you. And at this time, just wanted to end it with Dr. Williams, if she had any closing comments, but other than that.
Well, actually, Julie, looks like Julie's on. Julie, did you want to make any closing comments?
Her microphone is not active, and I don't know the number that her phone number is.
All right. Well, I will just close by saying thank you very much, Delores. I appreciate that. And I'll be thinking about this for the next few nights as I'm worrying over the power grid. And I'll try not to watch any more scary movies like Cobra on this.
Exactly. Yeah, I actually have a graduate student working on that topic now. So yes.
Thank you so much. We really appreciate it.
All right.
Thanks to everybody that joined.
And do feel free to share my email if there are questions that want follow up. I'm sure you'll send the ones that I didn't get to, and I will do my very best to get those answered. Some of the answers are I just don't know, but we're working on it.
Thank you so much.
Thank you. Everyone have a great day. And yes, I'll get you those questions and we'll get answers to those that had asked. Thank you so much again, and a pleasure seeing you. And anybody that has any questions directly, you can certainly email me at cindy.bonner@us.af.mil, and we can go from there. Thank you so much. Take care.
Thank you.